Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. Finally, now we are in Chapter 7. This is a chapter about quantum theory. So it's very different from all the previous traditional classical models we talked about. And quantum theory is playing a more and more important role in our daily life. You probably have heard about quantum computers, and they are working based on these quantum theories. So in this chapter, you probably are going to hear about all the crazy ideas that does not make sense to you before, but hopefully you can understand it better after study this chapter. The first video of chapter 7 will be the history of quantum theory. So in this video, I'm going to describe or introduce a few big names in the history that make significant contributions to the quantum theory. Let's start with the first one, Planck. You can see the picture of a young Planck and more senior Planck. He invented, or he is the originator of the quantum theory. He found that the classic theory to describe how things move in large scale doesn't apply to the atomic level. For example, here's an example of energy, right? So before the energy was smooth, the energy can increase from 1 joule, 1.1 joule, 1.001 joule, just name it. It's continuous. There is no gap between different values. However, in the atomic theory, energy was made of individual units or quanta. That means there are different, say, energy levels. There is energy level 1, energy level 2, but nothing in between. So it's discontinuous in the quantum theory. But here's the major achievement of Planck. He invented quantum theory. He is the originator of quantum theory. And as I mentioned, all of them won the Nobel Prize. So Planck won the Nobel Prize in physics in 1918. Second one is also very famous, Einstein, right? He developed the theory of relativity and laid the foundation of photon theories. In this chapter, we'll focus more on the photon series. And to be more specific, Einstein found the photoelectric effect. So this is device of photoelectric effect. What is exactly about is use a photon, a beam of light shining on this metal piece. And this metal piece can emit electrons and create the circuit using this device and can be detected. So in later videos, we're going to talk about this photon electron effect in more detail. So I'm not talking too much now. Also for Einstein, he won the Nobel Prize in physics in 1921. Okay, next one, Born. He developed the Born model of atom. This is also one of the important topics in chapter 7. We're going to talk about that in later videos. And he found that electrons are placed in and can jump between different energy levels. Remember the energy levels? We talk about on describing Planck. So that's the energy levels of Born model. But for his model, it's more, there's a limitation. We only describe an atom with one electron. Okay, if there are atom with multiple electrons, his model will not hold true. And he also won the Nobel Prize in physics in 1922. Compton, okay, he demonstrated the particle nature of electromagnetic radiation. Well, electromagnetic radiation is just a fancy way to say light. Okay, he demonstrated that light is not like just a wave. It's made of, it has some features of particles. So you can use a phrase to describe his contribution is he discovered the photon momentum. Okay, so then in the experiment he did, he found that X-ray, which is a very short wavelength of light, can scattered by free electrons. Scattered by free electrons had longer wavelengths and less energy. Okay, and this effect is attributed to the particle-like momentum to photons. So it's actually finding the particle feature of a photon. He won the Nobel Prize in physics 1927. And then 2 years later, de Broglie or you probably want to pronounce his name as de Broglie, but actually you can, it's a French name, I believe, and the L-Y-E can be pronounced as kind of Y, so it's like de Broglie. He found the wave theory of matter, and he won the Nobel Prize in Physics 1929. So the legacy or the story about him is he found this theory in his PhD thesis. It's not like others who established their own research lab and produce results from the lab. It's his PhD thesis. He predicted that the wave nature of electrons and suggested that all matter has wave properties. Previously, we talked about light is a wave, but it also has some particle features, right? From de Broglie, he predicts, well, crazy ideas again, everything has particle features as well as wave features. So I'm going to talk a little bit more about this de Broglie wave. So from Einstein, we know energy equals to mc squared. That energy is the total energy of a material, and that's defined by the mass of the material. Okay. And for light, we know energy equals to h nu. In our previous chapter, we talked about that. And that frequency of light can be replaced as c, the speed of light, over lambda, the wavelength of a light. And you combine these two together, you can see lambda equals to hc over mc squared. That equals to h over mc. Okay, so this is a description. This is the equation for light. mc. C is the speed of light. So for de Broglie, he thinks the lambda can also equals to h over mu. That u is the speed of any particle. When I say particle, I actually means like any object. It can be a book, can be a bicycle, can be a light, a photon, can be something else. For example, a human weighs 80 grams and runs at 5 meters per second. What's his or her de Broglie wavelength? A human can also have de Broglie wavelengths. Everything has a de Broglie wave. So we can plug in the number here. Lambda equals to h over mu. H is Planck constant. Plug in the number 6.626 times 10 to the negative 34th, and then divides the 80 kilogram, the basic unit of mass, and 5 meters per second, the basic unit or derived SI unit of speed. So then you can calculate the de Broglie wavelength for this human is 1.66 times 10 to the negative 36 meter. What does this mean? This means if a human runs at this speed and has this weight, then he presents some wave properties with a wavelength of 1.66 times 10 to the negative 36 meter. If this is a wave, then it can have all features of wave. So for wave, if you did this experiment before, it's a famous double slit diffraction. Okay, it's an animation of that. So basically, if you have a wave hitting on this wall and they are slit on this wall, as long as the slit is kind of close to the wavelength, then this wave can penetrate this wall and go beyond to the right space here. That means if this human is running and then there's a wall in front of him with the space of this 1.66 times 10 to the negative 36 meter, very small, but there is a possibility that this man can penetrate this wall. Crazy ideas, huh? So but anyway, just give you an example about how the de Broglie wave is calculated. And I highly recommend, strongly recommend you not to try this out by yourself, okay? Because you cannot control this wavelength, the slit with this length very accurately. So don't do that. Yeah. Okay, next one. Schrödinger. Well, you probably heard about the Schrödinger equation, and there's actually a company named Schrödinger after him. He also won the Nobel Prize in Physics in 1933, and he discovered the wave equation. Okay, to be more specific, he developed the Schrödinger equation. And this is the equation used very widely in the quantum theory, and it can be used to calculate the wave function of a system. We'll talk about wave function later, but you can treat that as the energy and the electron density and so on and so forth, include everything. Okay, all information is there in the wave function, and how the wave function changes in time. So you can use Schrödinger equation to calculate a feature, a property of a quantum system at a certain time, or you can also predict how it develops with time. So very, very big achievements. And Heisenberg, sorry, he discovered the uncertainty principle. Okay, he also won the Nobel Prize in Physics in 1932. He is known for the uncertainty principle, that is, the momentum and the position of a system cannot be measured accurately simultaneously. In the textbook equation 7.7, we can list the equation here. So what he found is delta x times the mass times delta u is larger than Planck constant over 4 pi. The delta x is the uncertainty in position. Delta u is the speed, right? So delta u is the uncertainty in speed. If the uncertainty in position times uncertainty in speed is larger than a constant, well, Planck constant divides 4 pi is still a constant. That means you cannot get both of them accurately enough. You know, the most accurate one is delta x equals to 0, right? Delta u equals to 0. The uncertainty is 0, that means it's very accurate. But if both of them are 0, you cannot make this equation work. So for that reason, you can either measure the position accurate, then your speed is inaccurate. And you can also measure speed accurate, then your position is inaccurate. So for the system, because there were so many researchers or scientists wants to discover or find the accurate position and accurate speed of a particle in the quantum world, and they cannot. And then now they find why, because of this Heisenberg uncertainty principle. You actually, by theory, cannot find both of them accurate at the same time. Please pay attention, simultaneously at the same time. Okay, so these are a few scientists, very famous scientists, big names in the field that contribute to the quantum theory. So I hope you know who they are and what their major contributions are to the quantum theory. I'll see you in our next video. Bye.